In this video, we will cover linear regression, how this algorithm is structured mathematically, and how we can implement it in Python from scratch. Hi, my name is Michael Attard, and I run a blog called Inside Learning Machines, where I discuss topics in data science and machine learning. My aim in this blog is to dive deep into machine learning algorithms and explain how they actually work. You can find a link to my blog in the description below. For any regression problem where a linear relationship exists between the predictor and target variables, linear regression can be a great choice for modeling the process. Linear regression is one of the simplest learning algorithms developed, and yet is also widely applicable to a range of problems, so long as the assumptions apply. I will first cover the key assumptions that underlie linear regression, and then we will work through a derivation of the linear regression algorithm using ordinary least squares. Next, we will take our derivation and implement it into Python code, and then verify that our implementation works. Now, if you stick around to the end of the video, I will also compare how our custom implementation performs against the linear regression model that is available through Scikit-Learn. So, let's get started. Now let's go over the key assumptions of linear regression. So the first and foremost is that there is in fact a linear relationship between the different variables in our data set. So we can look at two different examples here. In each example, we have a predictor variable, x, on the horizontal axis, and a target, y, on the vertical. Now you can see that in the first example, as x increases, so too does y, and we have this general linear trend in the data. So in this particular case, it's fairly obvious to conclude that there is in fact a linear relationship between the two different variables. So we meet this first assumption quite nicely. In the second example, there doesn't appear to be any obvious trend in the data. So as x varies, the y values on the vertical also vary, but there doesn't appear to be any obvious trend. And so in this case, we would have to cast some doubt as to whether there's any linearity at all. The second thing that we should check for is that the predictor variables are not correlated with each other. So in these two different examples, I just plotted the case where we only have one predictor variable, x. However, in general, we can have multiple different features that we combine together to determine a target y. And in this case, we need to be certain that these different predictor features are not correlated with each other. Now, the remaining assumptions that we're going to have here are all oriented around the residuals. So the residuals are the difference between a linear fit to the data and the true values of our target. And these consist of, the residuals should have a mean of 0, should have a constant variance, and they should not be correlated with themselves. So if any of these assumptions are not met, then we need to go back and rethink our approach to this problem. Perhaps we can do some data transformations in order to improve upon these results. Or in fact, we need to rethink whether linear regression is really a good fit for this problem. Let's move on now to a derivation of our solution. And more specifically, the type of solution that I'm going to be covering here uses ordinary least squares. And so when we make use of this, we will be able to come up with an analytical solution to our problem. So let's start off with just a general form. So linear regression assumes this type of relationship. So again, we have our target y that is related to a series of different predictor features, and these are these x's, which are subscripted with I and a second subscript that goes up to n being the total number of predictor features in our data set. These two are related with each other through these model parameters beta. And they go from beta 0 up to beta n. Beta 0 is our y-intercept term. And the I subscript just iterates through every single sample in our data. The eta term at the end is our error term. So if we show a plot, and these are the same data that I presented on the previous slide, but now I've included a linear fit to these data, we can see that the fit generally follows the trend in the data. However, the data points themselves don't all lie exactly on this line. There is some scatter around this trend line, and it is the difference between the trend line and where these data points actually are. Those differences are this eta term here. So that's this error term. So having everything written out explicitly per sample point with these I subscripts is kind of messy. So we can try to clean this up if we organize our model into a series of column vectors and a matrix in the case of the predictor features. So if we organize everything into these different objects, we can rewrite our original equation up here as a matrix equation. So that's what we have now at the bottom. So this is our linear problem that we want to solve. Specifically, what we want to do is we want to try and find the optimal values for our model parameters. That's this column vector beta. So that's what we want to be able to do. So on the next slide, that's what we will work on. So now what we're going to do is we will compute the sum of squared error. And that is given here. So sum of squared error is just the sum over the squared error terms. Now if we rewrite that in terms of vectors, what we have here is the transpose of the error vector multiplied by the error vector. Now if we populate these error terms in terms of the linear matrix equation that we solved for on the previous slide, we can get this expression. So now we have the sum of squared error written in terms of our model parameters and the data that we have for this problem. So now our next step is to compute the derivative with respect to our model parameters and then set that derivative to 0. So now we have this expression, and if we solve for beta, what we're going to get is this expression. And so now this is a solution to our problem, and it's quite neat because it is an analytical solution. So in the next part of this video, let's jump into a Jupyter notebook and implement this. Okay, we can start by running this cell. And here we just load in all the packages that we need. And now we can run make regression, and this is available from Scikit-Learn, to generate a dummy data set. So these data will consist of 200 samples with one predictor feature and one target. I'm also adding in here a y-intercept term of 50. And also we will be including some Gaussian noise with a standard deviation of 15. Now I'm also specifying that I want the true model coefficient to be returned, and that is just so that we can compare it with our fit later on. So let's run this cell. Okay, now we can make a plot of these data. And here you can see that although there is some scatter in these data points, you can see that it does follow a general linear trend. So this looks quite good. And now let's see if we can build a linear regression model that will accurately fit these data. So our implementation will be inside this class called LR. Now first we have an initializer function, and here all I define is an array that will hold the model parameters. Now the train method takes in as arguments an array of predictor variables and their associated targets. First, what we do is we add a column of ones, and that's simply to account for the bias term. And after that, in these two lines, all I'm doing is I'm calculating the optimal values for our model parameters. And this is determined by this function, which we worked out previously. So this is all that I'm implementing here, is just this matrix equation. Now in our predict method, I take in an array of predictor variables, I add a column of ones, and then I multiply the result by our model parameters to yield our predictions, which is yp, which gets returned. And finally, I added in another method, return b, and this is just used to return the learned model parameters. So now let's run this cell. And now we can test this out. So what I can do is declare an instance of our class, train it on the data that's available, and then I can generate predictions on the training data so that we can compare and see how well our linear regression model fits these data. Okay, now we can produce a plot. All right, and like before, we see that the blue scatter plot is just our data, and now superimposed on that, we have the results of our model, and this is shown in red. And you can see that the model follows the data quite well. So this looks like quite a good fit. Now we can compute the R2 score, and we get a result of 0.966. And the closer we are to 1, the better. So this result looks quite encouraging. It looks very, very good. We can take a peek at the learned model parameters. And if you remember, we introduced a y-intercept of 50. Here we see it as 52. This is reasonably close. And our model also says that the model coefficient should be 87. Now we can compare that with the true model coefficient. And the difference between these two values is quite small. So this looks quite encouraging. It seems like we've implemented linear regression quite well. And it looks like everything is working very nicely. So let's compare these results with what we could get from an out-of-box solution. And in this case, what we're going to do is we will compare our results with those that we can get by using Scikit-Learn. So Scikit-Learn has its own implementation of linear regression. So let's import that in now. And now we can just repeat the same steps that we did previously. So we can declare an instance, we can fit this instance to the available data, and then generate predictions. So we can do that. We can generate a plot like we did before. And we can see that this figure looks pretty identical to what we saw previously. Now we can generate the R2 score. Again, we get a result of about 0.966. And we can also take a look at the model parameters. You can see here, again, we have a y-intercept of 52 and a model coefficient of around 87. So this is very encouraging. It tells us that our implementation works just as well as what you could get from an out-of-box solution. And it's quite interesting. It's very neat that we were able to build a linear regression model from scratch and get exactly the same results that you would expect to get from an out-of-box solution. So if you enjoyed this content, please like the video or subscribe to the channel. All the code presented here is available on my GitHub. Please see the description below for a link to that repository. If you would like to learn more about linear regression and machine learning in general, please visit my site insidelearningmachines.com. I have included a link to my article on linear regression in the description below. Have a great day. See you in the next video.